accident and couldn't come to school, but he finally came.
Alright, this is the last video of the semester. This is the last chapter that we're going to cover, and then you guys have the privilege of taking your final. But let's get into chapter 10 first. So what we're going to do is we're going to continue on with bonding, how things bond, how things come together. But what we're going to do is we're going to add something slightly different at the beginning, and that's known as the Vesper model. So, I pronounce it Vesper. It's technically Vesper. It just stands for valence shell electron pair repulsion. And what the Vesper model tells us is the shape in 3 dimensions. So the 3D shape. And what regulates or what makes a 3-dimensional shape of a molecule is this repulsion of electron pairs, whether they be bonding or lone pairs. And so we'll talk about a little bit about this as we continue on. And so because of the repulsion, these molecules take on distinctive shapes. And I will tell you, this table 10.1, it might be kind of hard to see here in this context, but open up your book, look at table 10.1. It's going to be very, very important for what we're going to do. And so there's 2 different types of geometries. There's electron geometry, and then there's molecular geometry. We'll talk about molecular geometry or molecular shape in a minute. Molecular shape deals with lone pairs. Electron geometry deals with all pairs, whether they're lone or bonding. So, let's look at this table and see what it tells us. So, 2 electron groups. In this case, we happen to have 2 bonding groups with no lone pairs. The geometry is linear. Now, these 2 electron groups, they can either be a double or a triple bond. So on your guys' exam, I gave you this molecule. Right? So there's 2 electron groups. 1, 2. Triple bonds, double bonds count as 1 group. And so this bond or this geometry would be linear. The bond angle for something that is linear, that has a linear electron geometry, is 180 degrees, since a straight line has a geometry of 180 degrees. So, because a straight line, like we said before, the bond angle for that is 180 degrees. So let's move up one. So now we add a group. So there's 3 electron groups. Again, whether it's a single bond or a double bond, it's always so something like this would be an example of a double bond, but yet it has still 3 electron groups around it. This is known as trigonal planar. And we'll see these in 3 dimensions when we get to class. We'll do a little bit of a demonstration because what we're starting to do now is we're starting to talk about what we did in 2 dimensions, and we're going to start putting it into 3 dimensions. I'll explain why in a minute or later on. But the bond angle for a trigonal planar is 120 degrees. So let's bump up one more. 4 electron groups with just 4 electron groups. It doesn't matter how many lone pairs versus bonding groups. 4 electron groups for electron configuration is known as tetrahedral. The bond angle is 109.5. 5 is trigonal bipyramidal. So it's it's one pyramid on top of another pyramid. it's 120 degrees in what's known as the equatorial. So let's look at this blue center element with green around it. This right here is known as the equatorial, because as you can tell, there's 3 of these green elements that are flat. They're trigonal planar. That's on the equator. Whereas when I'm going to put this box around, the top 2 are known as axial. And these will be 90 degrees from each other. When we get to class, we'll talk about why things have to be this way. So, let's keep going. There's one more, 6. So we're only going to go up to 6 groups, because that's all that we've talked about. That's all we're going to talk about. This is known as octahedral. Everything is in 90 degrees. And so bond angles are determined by the number of bonded groups. Electron geometry is the same for everything that with 2, 3, 4, 5, and 6, independent of the lone pairs. So we should be familiar with these geometries. So what I want you guys to do to practice this, or just to look at it, it is in your book. I want you to go to table 10.1 and I want you to start memorizing these groups. So 2, 3, 4, 5, and 6. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. And then I also want you guys to memorize the bond angles: 180, 120, 109.5, 120, 90, and then 90. Because this will be very important information both for the final and for the quiz that you guys are going to have next Monday. So that's just for all the groups. We're not going to worry about the geometry. That's for the electron geometry. Now let's talk about the molecular geometry. Because the molecular geometry changes depending on the number of lone pairs. And so why would that be? So let's say we look at methane. Right, so methane. This is tetrahedral. And so the bond angle is about 109.5 degrees. Now, let's look at ammonia. So ammonia looks like this. Now, if we were to count the groups, we'd have 1 for the hydrogen, 2 for the other, 3, so 3 hydrogens, so there's 3 groups, plus the lone pair counts as a group, so there's 4. So, the electron geometry is tetrahedral, just like we see with methane. But when we look at the bond angle for ammonia, it's actually at 107 degrees instead of the 109.5 you would expect. And so let's look at another one. Let's look at this molecule we've looked at before. Water, right? H2O, dihydrogen monoxide. It still has 2 hydrogens, so there's 2 groups, 2 pairs of lone pairs, so there's 4 groups, so it's still, the electron geometry is tetrahedral. But if we look at the bond angle, it's actually 104.5 degrees. So what you can tell is as you add a lone pair, you start getting shorter and shorter bonds. So what can account for this? What can account for this are these lone pairs. Let's go and erase this tetrahedral. So these lone pairs are very repulsive because it's just a pair of electrons. They're not actually being shared between anything else. And so what these lone pairs do is these lone pairs push the bonding pairs down even farther, right? So instead of getting 109.5, you have 107 or 104.5. So what we've come up with is something known as molecular geometry. So, molecular geometry, we can see again on this table 10.1. And so let's say we have 3 electron groups, but instead of all 3 are bonding, we have 2 bonding with 1 lone pair. The electron geometry is still trigonal planar. The electron geometry does not change, no matter how many lone pairs we have. But what changes is this. The molecular geometry goes from trigonal planar to bent. And so here's sulfur dioxide is right here, and you can see it's not trigonal planar, but it's bent. So tetrahedral. So let's take ammonia, right? Ammonia has 3 bonding pairs and 1 lone pair. Electron geometry is still tetrahedral, but the molecular geometry is trigonal pyramidal. Water becomes bent. And so you guys should be familiar with these molecular geometries. With regards to the molecular geometries, you do not have to know the bond angles, or you assume the bond angles are those from the electron geometry, right? Because we don't know exactly how much they change. So here's the other thing. So let's look at the next 2. So 5 groups, right? 5 electron groups, 4 electron groups with 1 lone pair. You get this guy. It's known as a seesaw. I really like this one. But notice where you put the lone pairs on something with 5 electron groups. It's a little bit harder to see with this 2 because they turn it on its side. This is known as T-shaped. Notice 3 bonding groups, 2 lone pairs. It is not trigonal pyramidal, but it's T-shaped. Or it's not, it's not trigonal planar, but it's T-shaped. It looks like a T. You will need to know these for your lab the Monday after Thanksgiving, or the Thursday after Thanksgiving. So, 2 bonding groups with 3 lone pairs looks like this. It's linear, 180 degrees. But notice, so let's look at this. I will try to draw this as much as possible in 3 dimensions. So this is what we see with trigonal bipyramidal. If you add lone pairs, you have to add them to the equatorial position. You cannot add them to the axial position. There's not enough space between all of the different elements to accommodate that. So they have to be on the equatorial position. So then for 6, right, we can only add 2. So for 6, we add them to the axial positions, not the equatorial positions. So you get square pyramidal. So this is a pyramid with a square base, or square planar. So it's flat as a pancake, but it takes the shape of a square. So lone pairs can affect what we do. So, Chapter 9, we learn Lewis structures. Chapter 10, we're going to learn shapes. So, let's say I give you this molecule. Right? I give you this molecule, and I want you to predict the shape for this molecule. So we're going to have to go through, this will be 28, 35 plus 1 is 36 electrons. Right? So we're going to do the exact same thing that we did before with Lewis structures. So there's 8, so we'll put everything, we'll make octets. So there's 24, but we have 4 electrons left over. So what are we going to do with those extra 4? Well, let's look to see where iodine is. Yep, iodine is low enough on the periodic table that it can have an expanded octet. So, what's the electron shape? And what's the molecular shape of this molecule? So, electron shape, remember, just deals with total number of electron groups. So we have 4 bonds, 2 lone pairs, so that's 6 total. So this is octahedral. So the molecular shape of something with octahedral, with 6 groups, but 2 lone pairs, is going to be square planar. Right? So the whole point of me teaching you guys Lewis structures is to then determine what the angles and the shape of those molecules is. So why do we care? Why do we care about the three-dimensional shape? We care for a variety of reasons. One, because we want to know how these things look in space. Because in space, or in real life, they're not as flat like we draw them on the paper. Two, when you take drugs, for a variety of different reasons, so let's say you have a headache, and so you take aspirin. Aspirin has a specific shape. The proteins in our body need that specific shape of a drug so it can act on it, right? So we can start feeling better. And so those are just some reasons why shape matters. So, I want you to do number 35 and let's see, number 39. 35 and number 39, and I want you to do those. So let's see, today is Tuesday. I want you to do those by Friday, the 16th. Right? So number 35 and 39, I want you guys to do those by Friday the 16th. So, molecular shape, right? Again, why do we care about molecular shape? One reason why is because it can affect polarity. We talked about polar bonds in Chapter 9, but now what we do is we add a three-dimensional aspect to it. So, this is, if you're very familiar with vector theory, this has to do with vector theory. I'm presenting you guys this table for some common cases of adding dipole moments. Again, we'll need to know this for lab. But anything linear will not have a dipole moment. So for carbon dioxide, right? So here's carbon dioxide. So obviously oxygen is more electronegative, partially negative, partially negative, partially positive. But you can see it's being drawn this way and this way, so they cancel each other out. So it's actually nonpolar. If something is bent, the direction where the arrows are pointing in the middle of that is where your polarity is happening. Trigonal planar nonpolar, tetrahedral nonpolar, unless you have something like trigonal pyramidal, right? Unless you have that lone pair, right? We said water is polar because it's got 2 lone pairs. It's not officially geometrically tetrahedral. Molecular geometry is bent. So if that doesn't confuse you, just look over the table 10.2, and if you have any questions, then please, oh please, come see me. So we're going to talk about 2 more things. 2 more things left on the list. Valence bonding theory. We're going to talk about hybrid orbitals. So let's look at this. H2S. So hydrogen is this, but we've got 2 of them, right? Sulfur is this. So it's easy to see why this can come here, this can bond here, and they pair up and boom, we got a molecule. That's easy. Now, let's go in here. Let's keep the hydrogen circled. But let's change sulfur to carbon. So we're going to make this 2s, this 2p. We're going to do that. And so instead of H2S, we're going to look at CH4. So again, we got to add 2 more hydrogens. Well, we know this one can pair here, this one can pair here, this one can pair here. Oh, but wait. This one, let's do this in a different color. This one cannot pair there. Right? Because there's no other carbon electrons. So what in the world are we going to do? And so what we're going to do is we're going to take this S and these P orbitals and we're going to combine them. What do I mean by that? So, for carbon, we have 2S, 2P. And what we're going to do is we're going to combine these two and have a middle hybrid orbital known as an sp orbital. So this is sp3. This is known as sp3. So if you ever want to know what type of hybrid orbital we have, look at what you hybridize. 1s, 3p. So this is an sp3 hybrid. So sp3, as you can tell, because for CH4, let's say, CH4, how many things are going to be bonded to it? 4 of them. So sp3 hybrid orbitals lead to a tetrahedral arrangements. So you will also need to know these. So same thing with electron geometries and the bond angles. You need to know which hybrid orbitals line up with which electron geometries, and then you can, and then we'll talk about this. So, what I'm actually going to do based on the time is I'm going to stop here with sp3 orbitals, and in the next video we'll finish the 2 different bonding theories, because we're going to talk about different types of bonds. We're going to talk about different things that those bonds can do, and then we're also going to talk about the last and final bonding theory that we'll cover in this class.